Okay, so if there are no questions, then I will continue with what we were doing. So, right. So what were we actually doing? Okay, so let's go back. So, no, not here. Okay, so what is the question that we were trying to answer? So we have already constructed. See, as I mentioned last time, let me give this pointer again. So what we are doing is somewhat the more difficult part in a way. It may be a bit more involved part. So there are two things. One is, I mean, to the beginning part of the course, there will be two things. One is that we will work with measure spaces. It's kind of clear now. So one can just take measure spaces and start doing things with it, defining integration and studying the properties and so on. One can do that. That part is somewhat easier, I mean, but simpler. What we are doing, but all that doesn't make sense unless we have good examples. And Lebesgue measure is the first non-trivial example of measure. And that is underlying the entire subject, in fact. So what we are doing at the moment is to understand how measures are constructed. Okay, how non-trivial measures are constructed. And that part is actually a little bit on the tougher side, in the sense there are many ideas which will come and you have to wrap your head around them. So in the first shot, you may not get all the subtleties, in fact, but you try to follow as much as possible. So what we are doing is now in this abstract setting, so we have already constructed Lebesgue measure on the real line, but now we ask this following question, which is, we take some space X set. So some non-empty set, a collection of subsets of that, and a function from S to 0 infinity. Okay, and we let F be the sigma algebra generated by this collection of subsets. So we had two questions really. So what were the two questions that we had? Question one was whether mu extends as a measure to F. Okay, mu is a priori defined only for sets in this collection S. I want to extend the definition to sets in F which contain many more things possibly than in S. That's possible, but we want to do that. Okay, so that is one thing. Question two is the extension unique if it exists? Can there be two extensions? That is the question. Okay, so these were the two questions that we asked, and the answer to both was no in general. We saw that. But in the positive side, what we answered was, if S is here, we answered that if S is an algebra, then yes. This was only to the second question. So how did that answer yes come about? We saw that if two measures, so if there were two extensions to F, those are two measures on F which agree on the generating set, and the generating set is an algebra, then they have to agree on the entire sigma algebra. That is why there is at most one extension. So this is a very important thing. More important than this, I mean, the uniqueness is fine, it's important, but more important is the knowing the technique that we use to prove it. In particular, you should remember the monotone class theorem. The statement is important, which is very useful, as well as the technique of proof, which you remember was a little tricky. You have to show, I mean, you have to show something is a sigma algebra, some property holds for all sets in a sigma algebra or something like that, and then you reverse your viewpoint and look at all sets in the sigma algebra having that property and show that this collection is the sigma algebra itself, blah blah blah. So this is a standard trick of measure theory. If you have to get to grips with it to be able to do anything. Okay, so this much is done. So if S is an algebra, then the extension, we are not saying it exists yet. If it exists, it's unique. So in other words, there can't be two extensions. Now we come to the first question. Okay, so now we come to the first question and answer. Again, the amazing thing is the answer is yes, actually. But of course, here, what was the problem? So the answer in general is no, because no, if, for example, if ANs are in S are pairwise disjoint, and it's the union AN is in S. So this if applies to all this. So suppose there are sets which are pairwise disjoint in this collection S, whose union, there is no guarantee in general it is in S. I'm saying that if there are sets AN such that the union is also in S, they are pairwise disjoint and the union is also in S, and mu of A is not equal to mu of AN. Then, so the answer is no, because if this happens, then there is no way to extend. Mu as a measure. There is no way to extend mu as a measure, because simply it is clear that whatever be the you extend to a sigma algebra, the smallest one possible is this F. So you have a measure on the sigma algebra. Of course, it contains all these sets S. And ANs and A are there, and A is the disjoint union of AN. So this equality should hold. This inequality would contradict. So either you have to change the definition of the measure on some sets in S. So extend means, when we say extend, which means the measure mu is not, the definition is not changed on S. You have to keep the same values. You just define it for the new sets in F which are not in the original collection S. So then this is clearly a contradiction. So that is not possible. It turns out this is the only thing. So that is the key theorem that we want to prove now. So here is the theorem. Caratheodory's extension theorem. It says that, so let me just, so let's just use the notation A for S. So X, so A, an algebra of subsets of X, and F is the sigma algebra generated by that, and mu is from A to 0 infinity, included, infinity is included, countably additive. Okay, so what countably additive means is exactly that this happens, that whenever I could define it on any collection, okay, or maybe I just define it here. So in other words, that is a necessary condition for extension is that mu of A is mu of AN whenever ANs and A all belong to the collection. ANs are pairwise disjoint and A is the union of ANs. Okay, so this is what we mean when we say mu is countably, you have a function defined on a some collection of subsets. We say it is countably additive. So this, we will shorten it to say that this is said as mu is countably additive on S. Okay, so if this happens, whenever A is the disjoint union of ANs and AN and A are all in the collection, then mu of A should be the sum of mu of ANs. Then we say mu is countably additive on S. So a measure is nothing but a countably additive function on a sigma algebra. Only thing, when S is a sigma algebra, you don't have to say if A belongs to S. That is given. If ANs belong to S, A will also belong to S. Not a problem. So, but if you are talking in a general collection, then you have to impose the condition that A also belongs to the collection. Otherwise, mu of A is not defined. So that's the only difference. So now the Caratheodory extension theorem, I said that this is all that you need, that if this violation doesn't take place, in other words, if mu is countably additive, then it happens. No, that's not, I misspoke. You have to assume that that underlying connection is an algebra. Just like for the uniqueness part, if it's an algebra and you have a countably additive function on that, so then it extends to the sigma algebra. Extends as a measure to F. So when I say a measure to F, it means it extends to F keeping the countable additivity property. Okay. So some books use the word measure on an algebra and such things to mean this, but I just want to keep terminology clear. For me, measure will always mean on a sigma algebra. I will not use the word measure for anything else. Measure will be for something defined on a sigma algebra. And so if on some other collection I have that measure like property, I will simply say it is a countably additive function. Okay. So let's just to keep the terminology straight. That's all. So, but various books do say measure, if mu is a measure on an algebra, then it extends to a measure on the sigma algebra and such things. Yeah, so I will try to not use that terminology. Okay, so this is Caratheodory's extension theorem. So then we have a very nice answer. So of course, the countable additivity is necessary. And now it says that if A is an algebra, that's also sufficient. So that's a good thing. So, so just to give an example, we will see more examples, new examples later. But one example of something that we have already seen is, so let's take X to be the real line. And so A to be the algebra generated by LORC intervals, left open, right closed intervals. So what is the algebra generated by left open, right closed intervals, by the way? So you remember left open, right closed interval means it looks like AB. We also include minus infinity B and A to infinity and minus infinity infinity. Those are also allowed, but typical ones look like A to B, close open at A. So what is the algebra generated by that? Did we ever discuss that?
The Borel algebra instead of sigma algebra.
So the sigma algebra generated by it is the Borel sigma algebra. By the way, can somebody tell me why? I mean, so these are the, so let's call this, so let's give it a name. Okay, let's just spend a few minutes explaining this thing properly. So S is okay. LORC intervals are like this. Okay. So the sigma algebra generated by S we know. Okay. The sigma algebra generated by S is the Borel sigma algebra. Can somebody say why that is true? So let's just do that. Actually, I want the algebra generated by it, but let's first ask why is the sigma. What's the definition of the Borel sigma algebra? It is the smallest sigma algebra that contains all open sets. Okay, so it's the sigma algebra generated by open sets. So which is larger between the two? Oh, okay. you have to show, when you have to show two collections are equal, you have to show both way inequalities. Okay. So can somebody say why this is equal to B of R? What does an open set in the real line look like?
Left open, right open, like.
No, that's an open interval. But what does a general open set in a real line look like?
It's going to be a collection of intervals, I guess.
It is a
Bunch of intervals, union of intervals.
It's a union of intervals. More specifically, it's a union of any open set in R is a union of open intervals. That is true. Maybe a bit more specific. So first, so let us show this way inequality here. Okay, so whichever way. Okay, so let us. Okay, so first let me write the statement you said, which is that if A is open, then A is a union of, let's write Jn. Is it countably many or uncountably many?
I think that's arbitrary, right?
Uncountably many, right?
Possibly uncountably many. Okay. So what you are saying is a very general statement. So, okay, now I understand what you were trying to say. See, in any metric space, let's take any metric space. Suppose we had XD metric space. Okay. So, and let us take a set which is in X, which is open. Suppose G is an open set in X. What that means, by definition, means for each, the definition is that for each X in G, there exists a positive radius such that the ball of radius Rx around that is entirely contained inside G. Right? This is the definition of course, that radius I have written R sub X, it can depend on X, some other ball around some, so every point has a neighborhood which is contained in the set. So then we can write G as just the union over, you fix some R, any smaller R will also do, but let's say you have fixed some Rx for each X, then G can be written as the union of all these. Okay, this is exactly the equal because every X in G is contained in the corresponding ball. Okay, there may be other balls also which contain it, but it is certainly contained here. But each of these balls is a subset of G, so this is equal. So any open set can be written as a union of open balls. So what you are saying is somewhat like that. But isn't there something more specific you know about structure of open sets in real line?
It can be covered by countably many smaller open sets, in the sense that since there are countably many rationals.
So no, I didn't understand that. But let's say you are saying A is actually equals or contained in?
Equals.
A equals, you are saying countably many.
Yes.
Let's call it
because R is countable base, I think.
Huh?
R is countable base of open intervals.
Okay, so where so how do you argue this, that you can have countably many?
R is second countable, so I think it should follow.
You
Sorry.
can give a base for a topology, like all balls with all rational positions and rational radii.
Yeah, but okay. So, but can you? Okay, suppose you take. You are saying each Jn will be just an interval with a rational midpoint and a rational length.
Right.
We'll only take such things. But how can you write A as a union? Can you go over this reasoning and ensure that which X and Rx will you pick?
You can pick every x in G and Rx being a sort of a maximal.
But if you pick every x in G, it will become an uncountable union.
We can use the fact that the rationals are dense in the reals, right?
That is true, but how do you use that? Will there be rationals in your G necessarily?
No, but there will be a oh, okay.
It has to be, right, because rationals form a separable subset of R.
Okay, so there will be, yes, but is it enough to take? Okay, so the question is it enough to take balls of this? So for each x in G, I have this Rx. Is it enough for me to take this union over x, which are rational points inside G? Is that enough?
So we have to consider Rx also as rational.
Yeah, okay. Let's say there exists an Rx which we can say is rational. Okay, so now let me change it slightly. So there exists Rx in positive. So we can assume that it is a rational, no problem, because I can always decrease it. So can I take this? I mean, now I am taking in the real line. Is this okay or not?
We can definitely say that A is a subset of all unions of open rational, like rational open intervals.
But I am taking the centers only here. So the other way inequality is clear because each of these balls by choice will be contained in G. If the question is whether this happens. See, one has to be careful about the choice of Rx, right? Suppose I keep some, there is some number I don't like, 0, let us say, which is an element of G. And not 0, I mean square root of 2, some irrational number, which is, let's say, in G. But now for every rational, suppose I pick Rx so that the interval doesn't contain the square root of 2. I can always pick a positive number, right?
For every rational, you should pick the biggest one that fits.
So you have to do some such thing. Otherwise, you will not get. If you just say there exists Rx positive, it will not do. You have to take a large one. Okay, so that we are having an answer. But something even more specific is true when it comes to open sets in real life. What you say, so this is correct, but I want to say something even more.
Can we arrange them in order and then they become countable?
Which do you arrange in order? So this is countable is okay. Countable we sort of accepted. But I am saying there is something more true about the structure of open sets in real life, which you probably have seen. I mean, if you have done analysis course, you have seen for sure. So you can.
I think disjoint union.
Very good, very good.
Something like that.
Yeah, exactly. You can make it a disjoint union of. That is a very special property of the real line that you can write it as a disjoint countable union. Oops. J and R open interval. So this is a pairwise. So pairwise disjoint. Okay, so this is I mean, so you may know why this is true. I mean, so see, the point is for you take the maximal interval containing any point. Okay, so the way this works is for each x. Pick the So, I mean, I'm just recapping. This is not important here, but you should know this. I mean, so basic topology is very essential for measure theory. For each x in A, what we do is let AX be the, I mean, well, I don't want to write it formally. You consider all intervals all open intervals, fix an x, all open intervals containing x and contained in A. Okay, so you look at, so you pick a point X in A. Suppose I pick one point X in A. Okay, you look at all open intervals containing X and contained in A. There is at least one because there is some open interval around it. So take the union of these. Call it Ix. Okay, so what is Ix? It is the union of all open intervals which contain the point X and are contained in inside A. Okay, contained inside A. So, I mean, I should write contained inside. I mean here a subset contained inside A. So Ix is itself an open interval, right?
Yes.
It is an open interval and it is actually the largest open interval containing X and contained inside A. If I just said this, you might wonder whether such a thing exists or not. To show that there is a largest open interval containing X and contained inside A, you just take all open intervals that have that property and take the union. That will be an open interval with that property. You have to argue why that is an open interval. It's easy, but I will not do it now. So now you get all these IXs. These are the largest intervals possible. Now, if X and what you can say, if X and Y are 2 points, if X not equal to Y are elements of A, then either Ix equal to Iy or they are disjoint. Okay. See, Ix is some interval which contains X. X need not be in the center of Ix, it is there. Suppose Iy was like this. I am drawing below, so just for visibility. Is this possible that Ix and Iy intersect but are not equal? That's not possible because see this Ix is contained in A, Iy is contained in A. If this is the situation, the union is also contained in A. So why would I keep Ix? Ix would be the largest, right? So I would have taken the union for both of them. I would take this larger interval, that would be Ix as well as Iy. Not like this. So you argue that any two of these will be either disjoint from each other or they must be exactly the same. So now you are done. So you take these distinct ones and now you get now you have written A as a disjoint union of those intervals. There have to be only countably many. Why? If you write it as a disjoint union of intervals, it has to be a countable collection anyway. Because each of these intervals will contain a rational number and there are only countably many rationals, you can't have more than countably many disjoint intervals. Disjoint intervals. So that's the structure of real. So this is a special property of structure of open sets on the real line. Okay. You can't do this in the R2. For example, can you write open set a square? Open square as a disjoint union of open disks. Is it possible? Okay, I don't know why I asked this, but okay. So anyway, I don't need this. So that.
Sir, for some reason, I kind of feel this might have something to do with connectedness in one dimension versus connectedness in 2 dimensions.
Yeah, yes and no, yes, in a way. So, but it's so this theorem as written is not correct in 2 dimensions. Okay, so you cannot write it as a I mean, there are some substitute things which will be good enough for measure theory purposes, but topologically this is false. Such a thing, you cannot write it as an open, disjoint countable union of open balls.
Right.
That fails. But let's stick to the special case of real line and work here. So this was just a recap actually. I mean, so since everyone did not seem familiar, I thought I'll recap. But let's come back to our question, which is X is real line and I take the algebra generated by left open, right closed intervals. And now question is the sigma algebra generated by them is the same as the Boyle sigma algebra of R. And this fact we will put on the side. So now we want to prove this. So I want to just quickly argue this. Can you say why sigma S is contained inside B of R? And then you will tell me why B of R is contained inside sigma of S. We'll have to prove both. Okay, can someone say why sigma S, the sigma algebra generated by S is contained in the Boyle sigma algebra of R? How do you show that?
I think you can make any open interval using these left open, right closed intervals.
Okay.
And then that
You are
force-
saying any open interval can be written in terms of left open, right closed intervals. Okay. Will that be the way? I mean, so which one? You are saying sigma S is contained in B of R, right?
Actually, I think that'll show the other thing.
Okay. So for this, what do you want to do? Maybe the other way. Can you write these in terms of open intervals? So you take any of these, take any element of S. Is AB itself in the Boyle sigma algebra?
Well, we can take open A to open B plus 1 over n and then just take intersections because all of these are going to be in your Borel sigma algebra. So their intersection better be in the Borel sigma algebra.
So instead of doing what you said, I wrote it as union. Not a big problem, right? So AB, I can write as the, oh, sorry, you want close one. You are right. So I have to take the intersection. That's not, and this is plus. You are right. So I should do what you said. B plus 1 by n. Let's take the open interval and take the intersection. Okay. Similarly, for minus infinity B, A infinity is anyway open, minus infinity is open. Minus infinity B can also be written like this, right? So what this shows is, this shows that, see, these open intervals are definitely in the Boyle sigma algebra. Boyle sigma algebra contains all open sets, so it contains open intervals. So this shows that all elements of S are also in the Boyle sigma algebra, right? So I just wrote it for this AB, but A infinity open is anyway there, minus infinity open is there, minus infinity B is similar like this. So this shows that my generating collection definitely is in the Boyle sigma algebra. So that certainly implies that, but this is a sigma algebra. Therefore, the sigma algebra generated by that is contained in the Boyle sigma algebra, right? So if you find any sigma algebra containing your collection, the generated sigma algebra can only be smaller than that. So that's all. Okay. So how do you go the other way? How do you show that Boyle sigma algebra is contained in sigma of S?
This would be what you wrote earlier, the union.
For the union.
So you take any open set. If A is open, implies A is a disjoint union of, these are open intervals. Okay, so now what? What does this show?
Shows that the open intervals fall inside the sigma algebra of.
No, it does not show anything yet. See, what is the sigma S is on the right side. So you have to still write these open intervals in terms of S.
So Jn is let open An comma Bn. So
Yeah.
we can replace An comma An by open An close Bn.
So if Jn is An comma Bn, you can write this as a countable union of An Bn minus 1 by K, let's say. K equals 1 through infinity. So you can write each open interval as a countable union of this. So what this implies is that Jn belongs to sigma of S for all n. But then a countable union of those things will also belong to sigma of S for all open A. So that is sigma S contains all open sets. But the smallest such sigma algebra is the Borel sigma algebra. Okay. So yeah. So I mean, I'm going slow. I mean, just I wanted to do some small simple things also like this. So this is the type of reasoning you have to do to solve many problems. You have to write out clearly. If you have to show two sigma algebras are equal, you have to show one is contained in the other is contained in this. And you have a lot of flexibility, by the way. Don't try to take the worst possible set here and directly try to express it in terms of the generators. There, nothing like that is needed. So, for example, you have to take an open. So you don't know what Borel sets are. You can't say let A be a Borel set and try to show it is contained here. You don't know anything about a Borel set. All you know about Borel sigma algebra is it's the smallest sigma algebra containing open sets. So you should say let A be an open set. So if you show all open sets are here, that will work. But if you try to show, say, let A be a Borel set and try to show it's in sigma S, you will never be able to do because you can't write the Borel set in terms of anything. Okay, so that's those points you have to pay attention to. Okay, so this was just as a warm-up exercise to show sigma S is B of R. Let's go back. Any questions about this so far? What's the algebra generated by S, by the way?
I think it would be finite unions of left and right close.
The set of all the finite unions of finite disjoint unions like this. So this is not true for every S. This is for S, which is collection of left open, right closed intervals. Okay. So I'm saying that. So this is just to tell you another point that I made. I mean, I emphasized time and again that sigma algebra generated by collection is very inexplicit. You don't have representation for the sets in the sigma algebra generated by a collection usually. But the algebra generated by a collection is actually usually very explicit. So in particular, it's very clean for something like left open, right closed intervals. If I take that, the algebra generated by it consists of all finite unions of pairwise disjoint LORC intervals. That's all. How do you show this? How do you show such a thing? First of all, you have to check if this contains all the intervals, right? I mean, when K is 1, it contains LORC intervals. So how do you show this is, if you show this is an algebra, it's also clear that, okay, what is clear that, okay, so so the algebra generated by S should contain each of the LORC intervals and also finite union. So it is clear that all these sets should be in the algebra. But if you can show this collection is an algebra, you are done. So check that this collection is an algebra. I'm saying that if you check that this collection on the right side is an algebra, then you have shown that that's the algebra generated by S. Because it can't be any smaller than this, because the algebra generated by S will have to contain all this, that is clear. So what if it's itself an algebra, then you're done. So how do you check it's an algebra? It contains empty set. I put K equal to 0 also, that's the empty union that is there. It complements, that is the key point. So if you take complement, what happens? The key point, I will leave it to you. Okay, I will leave it for you to check. The main point is AB complement is minus infinity A union B to infinity, which is a union, disjoint union of two sets in S. They are both LORC intervals. This is what goes wrong if you consider closed intervals or open intervals. Then it's not so clean. The complement will become complement of open interval will be like not two open intervals, not at all. I mean, there will be two closed intervals. So that's a pain. So it's much cleaner with LORC intervals. That's all. It's not that you can't work with open intervals. You can. It's just a tad more complicated. That's all. So this is simpler. We stick to that. So anyway, so going back here, what is the Caratheodory extension theorem? So what was the Lebesgue measure situation? So to construct Lebesgue measure, on R, we start with lambda. So I know how to define lengths. I mean, I'm just repeating we already constructed Lebesgue measure. I want to just view this in the light of this theorem. How is this theorem saying anything? So we know what lengths of intervals have to be. Hence, I also know what it has to be on this algebra, right? I know how to define it by lambda of any set here is of the form I1 up to Ik, the disjoint union of those. I'll define the length of any set, lambda of any set, to be the sum of the lengths of these, because this is also a disjoint union. Okay. So now this is not the way we did it. So that's what I am saying. It is a different perspective of something we already did. So then, according to Caratheodory extension, it says that you have defined like this on this elementary sets. Now all you need to do is to check that lambda is countably additive on A. Okay, is countably additive on A. Then Caratheodory tells lambda extends as a measure to sigma of S, which is in this case the Boyle sigma algebra of the real line. Okay, so this is another viewpoint of how that thing works. This is not the way we went about the proof. You may ask, where in the proof did I check countable additivity? We did not do it that way. Okay, I mean, it was maybe implicit but not explicit. So, but this is the general viewpoint in Caratheodory, that you have a small class of sets which can be explicit, like algebra generated by intervals, on which you have the notion of measure or length or area, whatever you want to call measure, which has to be you have to check that it has this good property of countable additivity. Then it automatically extends to the sigma algebra generated by them. Okay, so that's it. So that's the way. So of course we didn't do it that way, but now let's go and prove Caratheodory extension theorem. How to check that lambda is countably additive on A? Is it easy? It's doable. Okay, so we'll come back to that point later. Okay, any questions? Sorry, what I wanted to do was, after stating the theorem, I wanted to give an example with illustration. There were multiple digressions here. One is into this representation of open sets. Another is into the algebra generated by it, the sigma algebra generated by this, and so on. But modulo that, all I did was I illustrated this theorem with the example we have already seen. That's what I did now. Okay, any questions? What I want to do is prove Caratheodory's extension theorem now. And then next time we will see many other examples. For example, Lebesgue measure on RD, measures on Cantor set, and other examples which we can, once you have this, you can get them. Okay. Okay, so if you accept this, but there are a couple of questions you may still have. Our earlier extension extended it to something called Lebesgue sigma algebra, which was actually larger than the Boyle sigma algebra. Here, Caratheodory extension seems to give to a smaller sigma algebra. Now, one point, Boyle sigma algebra is good enough. We don't have to be greedy. This is good enough. But secondly, actually, this is the way I stated it here. But when we prove it, we will actually extend this measure to a larger sigma algebra. In fact, okay, so that feature will be there, but we will come to that. Okay. Now I want to go to the proof of this theorem. So it goes over many steps. So there are many things to do to prove Caratheodory extension theorem. Much of it is a repetition. Some of the steps are exact repetitions of what we have done before. Nevertheless, let's go over it. It's like a recap of some of the steps. Some steps are new and maybe it sheds new perspective. Maybe you'll understand it better second time. So it's not checking countable additivity. Let's just prove. So this is a very powerful theorem. After this, you are fine with constructing measures. This is pretty much all you need to know to construct measures. All measures are constructed usually by these methods. Okay. So what is the method? So the step 0 is the following. So what we are starting with. So let's recap the setting. X is a set and A is an algebra. Actually, for that matter, it doesn't have to be an algebra at the moment. Okay, so let's anyway write it. It's okay. And we are given mu from A to 0 infinity, which is countably additive. And the goal is extend mu to the sigma algebra generated by this algebra. Okay. Now that goal will be reached ultimately. Don't try to focus on it too much. So how do we go about it? So step 0 is this. So we define, what did we do in the case of so in the case of Lebesgue case, we defined an outer measure. You remember? So remember that we defined an outer measure. That is what we are going to do. So define mu star from 2 to the x to 0 infinity. For every subset, we are going to try defining a measure. Okay, trying defining its length, area, whatever it is, using mu. Mu is given only on the algebra, but we will try to define it on for all sets by, how do we do? Exactly like we did for Lebesgue measure, but except that algebra will take place of the intervals. That's all that happens. Mu star of any set A is defined as the infimum of, we'll just cover this with countably many elements of the, so where ANs are elements of the algebra, ANs are elements of the algebra, and union AN contains my set A. Okay, so too many A's, so let me call it B. So mu star of a set B is defined as, so you just cover it with any countable collection of elements from the algebra. Okay, and then we define the outer measure of it by taking the infimum of the sum of the measures. Mu of AN is well defined because mu ANs are in the algebra. Okay, so the key point to notice is that this is the step 1. So I'll write 3 properties which I had written earlier. So one is mu star of empty set is actually 0. Property 2 is that mu star of A less than equal to mu star of B if A is contained in B. And 3 is mu star of union AN is less than equal to summation mu star of AN. Okay, for all an which are subsets of X. So three properties are true for mu star. They are all easy. So the second one, this is monotonicity. So and this is countable subadditivity. Okay, so why are these two? Empty set, it is clear. You can just cover it with mu of, by the way, mu is countably additive on the algebra. It implies immediately that empty set has to get zero measure, by the way. Because empty set union empty set is empty set. So mu of it is, mu of empty set is 2 times mu of empty set. So that is there. So this is trivial. First property is trivial. Second one is also easy because if A is contained in B, any cover for B is a cover for A. So any countable cover for B is a countable cover for A. So the infimum for B, infimum for A is over a larger collection. So the infimum will be smaller. So this goes this way. And countable union is also fine because if I get, if I can cover each AN by a countable union of algebra elements, then I can use this entire countable union of countable collections to cover the union. Okay, I don't know if you want me to explain this, but the proof is exactly the same as before. Okay, here, the main point is any cover, countable cover for B is a countable cover for A. Therefore, this is a large infimum over a larger sets, larger collection of numbers. Therefore, that is the. Here the point is, if okay, let me just write it out just once. Okay, so I can leave it, but the point is, you can always find if see if one of the mu star n is infinity, then nothing to worry about. Okay, so let's write it for the case where mu star n is all finite. Otherwise, if one of these is infinity, right side is infinity, so no problem. So otherwise, so I will not write all that here. So I'll just say find some sets, call it C and J in the algebra such that that's a cover. If I take C and J union over J, that covers my set AN. And if I take the sum of the measures of those things, or sum of whatever the original mu of those things, since the infimum is supposed to be mu star of AN, is less than mu star of AN plus epsilon. But you remember, I should give myself a little more room, a little less room, epsilon over 2 to the n. Then, if I look at C and J, varying over n and J, it is a countable cover for union AN. And if I add the sum of lengths of all this, I call it length, what I mean is mu of C and J, then I get this less than equal to mu star of AN plus an epsilon outside. So that's why you get a countable cover for union AN, which has total sum of lengths less than this plus epsilon. That means this infimum mu star is less than equal to this one. That's the proof. Okay, so this is how monotonicity, countable additivity are immediate actually. So what did I use here? I did not use the fact that A is an algebra. I did not use the fact that mu is countably additive. Actually, I didn't use anything. So if you notice, we did not use either for now, neither of these was used. Right? Where did I use that? No, not at all. So this is fine. So far, this is okay. So anyway, this is the general definition of a outer measure. Any function.
Sir?
Yes.
When we say that the infimum of such a cover, the fact that such a cover exists kind of uses the fact that X itself belongs to the algebra, right?
Right. Yes. So this is a good point. This infimum is not an empty infimum. It is an important point. This is not an empty infimum because I can take A1 to be X itself because the algebra always contains the set X. So I can take A1 to be X itself and then the rest of them to be empty. Of course, this can be infinity. That is okay because mu of the X could be infinity. That is possible and we allow that. Mu star of B also could be infinity. Yeah. But it's a good point. This is not empty infimum because always there is a cover by X and a bunch of empty sets.
Which depends on the fact that A itself is an algebra.
Okay. You are right. So that is true. So if I say that it is in general, but it doesn't, okay, it doesn't really use algebra. We just need that you should be able to cover, right? I will still stick to my claim, which is in your view of what you are saying. In the literal sense, what I said was not completely valid, but it requires very little. I should have said that maybe the collection contains X or something like that. Okay, you are right. You are right. So, but I'm not strictly using algebra property and countable additivity property in this. That's all I wanted to say. Okay. Yeah, but point taken. So, any function mu star from the collection of all subsets to 0 infinity satisfying 1, 2, 3 is called an outer measure. So what we had earlier was called Lebesgue outer measure, but this is a general outer measure. Okay, so an outer measure need not even arise from a mu like this. I didn't say that. I mean, this is one way. If I start with the mu, which was my problem, I start with mu defined on an algebra and all that. But in general, you can just think of any function defined on all subsets, satisfying monotonicity, countable subadditivity, and that empty set gets 0. That is called an outer measure. Okay. So any questions? So what we are going to do is now I go steps. So this was step 0 in getting to the Caratheodory theorem. How we go? So from mu we got a mu star, an outer measure. Now what I am going to do is very much like in the Lebesgue measure case. Whenever I have an outer measure, it need not even come like this. You just take an outer measure. We will define like Caratheodory defined, Caratheodory cut condition. We will define some class of sets as somehow nice. Okay, and that will be the where we will restrict the outer measure and then it will behave nicely. That's what we will do. Okay, so that is the next step. Next step.
Sir, what is the difference between this outer measure and Lebesgue outer measure?
So this is on any X and any, I mean, so this can be Lebesgue outer measure is an example of this. So Lebesgue outer measure is an example of this when X is real line and a particular way of defining it was chosen. But there are many outer measures which we can get from, I mean, this can be on any set and there can be one, I mean, so if you ask what are the examples, you can start with any mu defined on an algebra. And as I said here, so you take a real line itself and you take any function. So for example, so just to give a very concrete example, you could take the X equal to real line and A as before, algebra of left open, right closed intervals, and mu of mu of anything here I know how to define, so let me just define mu of I. Mu of I, let me define to be square of the length, suppose, or square root of the length. So what is mu star in such cases? So you get an outer measure. So I'm just telling you that you can think of this example. So you can start on the real line with on intervals I define mu to be the square of the length or the square root of the length. Then you get a different outer measure. So I leave it for you to figure out what that outer measure is. In this case, it's not a very interesting one. Okay, but nevertheless, there is such a possibility. You can define it as anything. You can define mu of I to be anything, whatever you want, and you get a mu star. That will give you a different outer measure.
Yeah, okay.
Okay, so now, so the second step, let mu star be an outer measure on X. It doesn't have to have horizon like this, but that's the example we're interested in. But mu star can be any outer measure on this. Now we will define what is the class of measurable sets. Okay, so we define say that A contained in X is mu star measurable if the Caratheodory cut condition holds. Mu star of A intersection E plus mu star of A complement intersection E equal to mu star of E for all subsets of X. Okay, so that's how we define it. So remember that this way is trivial. It is this way that is questionable. Is it true? Because subadditivity tells you that this union of these two will give this. So therefore, mu star is less than equal to sum of these two by the countable subadditivity. But it is the other way inequality that is being a condition, not trivial, meaning questionable means that is the non-trivial condition here. Okay, that's the non-trivial condition. And if A satisfies this, then this is called mu star measurable, and the collection of all mu star measurable sets, let's call it L mu star. Okay, so what is the idea? Again, just like with Lebesgue measure, so now you have mu star defined on all the power set. Suppose it is countably additive on the power set. In the sense, if you take disjoint sets, the mu star of the union is sum of mu stars for countably many disjoint events. If that was true, then mu star would be a measure on the power set of X. Perfect. I mean, that would be fantastic. I mean, wonderful. Okay, so if you feel that way, then you should wake up because you are dreaming. That is usually not going to happen in real life. So on almost no self-respecting outer measure is going to be countably additive on the power set. Okay, so that is a pipe dream. So what we have to do is we have to restrict to a class of sets on which it will become a measure, and that restriction is to this class of sets that Caratheodory identified. So you have to restrict to a sigma algebra where it becomes a measure. Now this is what Caratheodory came up. And last time somebody asked this question: what is this Caratheodory condition? How do you explain it? Actually, it is a very clever condition. It's not easy to explain it. See, what is happening is because it is, I mean, to give maybe a stupid analogy, but there is a large group of people maybe. If I tell you select a large group of tall people out of this group, this is easy. You go to each person, you have some criterion for tallness, you take them or not take them. That is good. But if I tell you there is a large group of people, you select a large subgroup of them who are friends. How are you going to do that? This is a kind of problematic thing because whether you pick a person depends on whether he or she is friends with the others you pick. And that depends again on who you pick. It is a self-referential thing which it is not clear how to go about doing it. Right? I mean, you have to pick a subcollection who are friends because the point is, unlike tallness, which is a property of a set person, friendship is a property of the interaction between two people. So here what we want is the countable additivity. It is not a property for a set. I mean, if you fix the mu star also, it's not a property for a set, but how it goes with other sets. So how do you get these people who are friends? Caratheodory's nice way of breaking this circularity is that if you put this condition, it breaks the circularity. It is a clever thing. I cannot explain it further, but that is where the cleverness is. Now the claim after this, the claim will be, the big claim is this.
Sir,
Yes.
I have a question.
Say again. Can you
Sir,
say
I have
again?
a question.
Yes.
I'm saying, is this the largest class of sets where mu will be a measure?
No. This was asked in the case of Lebesgue also. I don't think that is true. You can add some more sets. It's possible. Yeah.
Okay, thank you.
So I don't think that is true. That is not exactly correct. To my knowledge, it is not true. Maybe I should find example and say how to put it, how to do it. But it is not true. So it's not largest, but here we have. It's not a question of being greedy to get all of them, but if it is large enough, we'll be happy. Actually, for now, you should not worry whether it is whether you get everything, whether you get anything is the question. For all we know, this L mu star could be just the smallest sigma algebra of empty set and the whole set. That can happen actually. Okay, we'll come back to that. That is actually the big problem. So, but let me say the claim. What is the claim? Once you do this, the claim is L mu star is a sigma algebra. And mu star, if I restrict to this, is a measure. This is the claim, that this is a sigma algebra and this is a measure. So here I'm just starting with an outer measure. So whether it agrees with mu and so on doesn't come here. So here I'm starting with just an outer measure and taking a subclass of measurable set. So all I'm saying is that's a sigma algebra, and restricted to that, the outer measure becomes a measure. Okay. But for all we know, this could be very, very small. This could be trivial, empty set, and it can happen in many situations. We'll come to that later. But now this is the key thing to prove. But then the big question will be, I don't want this to be too small. I want this to be big. How do I ensure it is big? Then we go back to this situation. If I start with a mu star which arises from a mu which was countably additive on an algebra, then so let me write that third step also so that we have the entire thing clear, and then we can go about proving things. So if mu star arises from a mu that is countably additive on an algebra, okay, so that means so mu was originally defined on an algebra and mu star was defined like this with the infimum thing. If mu star arises like that, then we have good things to say. First of all, L mu star will be large. It won't be too small. It will at least contain my entire algebra. So which means that it contains, it's the same as saying it contains the sigma algebra generated by that, because it's a sigma algebra. Okay, so it will be a largish sigma. If depends on your algebra, but you can't expect more than this. You have defined starting with an algebra. Your L mu star at least contains all of them, and hence the entire sigma algebra generated by them, because I know L mu star is a sigma algebra. But also another nice thing, and mu star equal to the original mu on the algebra. So it is actually an extension. So mu star, when you go from the mu to mu star, you did not change the definition on the algebra. This was something we checked in case of intervals, that the outer measure was equal to the same as the usual length of an interval, right? So that is the point. So that is also preserved here, that if in the case when mu star arises from a countably additive measure, countably additive function on an algebra, our sigma algebra of measurable sets is not too small. It contains the entire algebra, and mu star also doesn't change from the mu on the algebra. Elsewhere it is extended. So it's an extension of the measure. So that's why it's an extension. Okay. Any questions about this? With these three, you are in a good shape. So you get a measure. This completes the proof, right? I have not proved either of these two statements. So this is claim 1, this is claim 2, both have to be proved. So let's call it claim 1. And this is claim 2. Both need to be proved, but once you do that, your extension theorem is in hand. Any questions about this? Is it clear? I mean,
Sir, what was the exact question? The question just talked about extending mu, but to what sigma algebra? I mean,
okay, I extended so good. So the Caratheodory extension theorem said that, I mean, when I stated it, I said that it extends it to a sigma algebra, which is at least the sigma algebra generated by A. Okay, I mean, you have said it extends to a measure on A, on sigma of A, right? Okay. What I have now said is that it actually extends to this L mu star, some mysterious sigma algebra, which contains sigma of it, which is good for me. I can, if I have measure on a larger sigma algebra, I can always just restrict myself to the smaller sigma algebra, not a problem.
Yeah, got it.
So it is an extension to an even larger sigma algebra. Typically, there will be, just like with Boyle sigma algebra, in the example, if you see, this sigma algebra generated by left open right closed intervals is the Boyle sigma algebra, but the other one was Lebesgue sigma algebra. We haven't shown, but it is actually, they are not the same. The Lebesgue sigma algebra is slightly larger, somewhat larger. So we'll come to that point later. So I have, so, but in general, it's a bit larger. But the one thing about that's correct. But the nice way, why state it in this limited way? Why not say goes to the more general one? Okay, just let me explain this point here. Maybe I will explain again when it comes. The nice thing about this F is it depends only on the algebra A, right? I have an algebra A and I have the sigma algebra generated by A. For example, if I had left open right closed intervals, F would be Boyle sigma algebra. Fine. Then any countably additive function on this algebra extends to this sigma algebra. That's what Caratheodory says. But what about this larger one? This larger one depends on the particular mu you pick. Okay, this L mu star. So if you start with different mu on the same A, they give rise to different sigma algebras L mu star. Okay, if I have mu1 and mu2 are two countably additive functions on, let's say, left open right closed intervals, that algebra generated by that. Then mu1 will go to an outer measure mu1 star, mu2 will generate an outer measure mu2 star. But then there will be a sigma algebra L mu1 star and a sigma algebra L mu2 star on which you will extend. Both of them will contain the Boyle sigma algebra. That is correct. But they are actually different. So this is the one advantage of sticking to Boyle sigma algebra is that it is one common sigma algebra, whereas these other L mu stars, they are larger, but they depend on the mu also. That's the point. So if I want to talk about
just one.
Go ahead.
So, sir, at least both of them will agree on sigma algebra generated by A, right? The mu1 star and mu2 star.
Talking about two completely different measures. See, okay, no. So if you start with mu, then you get one unique extension that we agree. No, now I'm making a different statement. There will come a situation when I may be interested in a lot of measures, not just one measure at the same time. So if I start with two different mu's, so let's say mu1 and mu2 are two different countably additive functions on S. Okay. So for example, I gave here a stupid example, but let's stay with the stupid example. On the algebra of left open right closed intervals, I have three possible things. Okay, these are not additive, so it's not good. But sorry. No, let me not give that example. So on a given algebra, I may have two different ways of measuring lengths. Their purpose may be different, completely different. Okay, so let's not worry why we want that. So I have two different mu1 and mu2 on A. I want to extend both of them. I'm saying that if both of them are countably additive on the algebra, then they both extend to the sigma algebra generated by the algebra. But this other larger sigma algebra, L mu star, will L mu1 star will not be same as L mu2 star. So then they will be on two different sigma algebras. So if I want to add two measures and such things, then I would like them on the same sigma algebra. Then I stick to the smallest one, namely the sigma algebra generated by A. That's all I'm saying.
Yeah, got it. Thank you.
Okay, any other questions? Okay, if not, let's go over the proof. The proof is almost completely, almost like before. Maybe I will do the proof of claim 1. Maybe I don't know whether the proof of claim 2 will have time. If not, it will spill over to the next time. So proof of claim 1. So forget all this thing in red. So you have an outer measure and we have this notion of Caratheodory cut condition. I didn't say this. This is the cut condition. So from the cut condition, so there is nothing else you need to pay attention to in this page. Mu star is an outer measure. Outer measure means it satisfies these three properties. Now we say that L mu star is the collection of mu star measurable sets, which is those sets which satisfy the cut condition. Then the claim is that they form a sigma algebra and mu star restricted to that is a measure. There is no claim on how big this is and so on, but let's not worry about that. In general, we can't even say. So how do we say that L mu star is a sigma algebra? Okay, first, empty set belongs to L mu star. Is that okay? Because, okay, so anyway, here the only need to check, let me write again, only need to check less than equal to here, okay? That's how I always do. Okay, anyway, so empty set is there because you take any E. For any E, what is mu star of E intersection empty set is, it's mu star of empty set which is 0. E intersection empty set is empty set which is 0. Mu star of E intersection empty set complement is just empty set complement is the whole set, that is just mu star of E. Therefore, the sum, so now you see that the cut condition is satisfied. The sum of these two is mu star of E, right? So this proves that empty set is in L mu star. It satisfies the cut condition. Another thing which is trivial is that if A satisfies the cut condition, then A complement satisfies the cut condition. That is very clear from the symmetry of A and A complement in this statement, right? This is same. You just reverse the roles of A and A complement. So that's also clear. So two parts are clear. How do you go about checking countable union and such? You remember the proof? So first, what is it that we did first? The steps are identical almost actually. It's actually all almost exactly the same in fact. So do you remember what is the next thing you would do if you have this situation? You have to show L mu star is a sigma algebra. The next simplest was to do the intersection. That's what we did. There are many ways to go about it. We will go about it like this. Intersection of two things. So we want to show that if, let's prove this, that L mu star is closed under finite intersection. Okay. So what should we do? Take any A. Take any subset of X. Then we can use the cut condition to do that. So E is any set. We can use the cut condition on A because A is nice, A is measurable in this sense. Mu star of A will be mu star of E intersection A plus mu star of E intersection A complement. That we know. Now we further do an intersection with B. This one I can write as mu star of E intersection A intersected with B plus mu star of E intersection A intersection with B complement. That is for the first. So this is, I'm just doing ED intersection A, I'm decomposing like this. Okay, so these two, this is all coming from the first one, and the last one remains as it is. Okay, the intersection A complement, that stays as it is. So now what? So one set is what I want, E intersected with A intersection B. So the first set is E intersection with A intersection B. Now what about the union of these two? What is the union of these two? E intersection A intersection B complement and E intersection A complement. That means these are elements of E which either don't belong to A, or if they belong to A, they don't belong to B. Right? So they are elements of E which should not belong to both A and B. That's what. So by countable subadditivity, this is greater than equal to mu star of the union of those two is exactly E intersection with A intersection B complement. Right? Elements of E which either don't belong to A or belong to A but don't belong to B. That means they don't belong to the intersection. So this sum by subadditivity. So we got what we want. Mu star E is greater than equal to. So what we have shown is mu star E is greater than equal to, with, if I call C is A intersection B to save writing, we have shown mu intersection E intersection C plus mu star of E intersection C complement. Right? That's it. So implies C is in L mu star. So that proves that intersections are there. Okay, so how much time do I have? Okay, I have a few minutes. I can finish this. Not only that, we also see something. Okay, so next I want to show, also we make an observation about mu star.
Sir, actually, hello. This is the part I couldn't follow even the last time. So, I mean, ultimately, we want to show that that is a countable subadditivity, right? So, how are we showing this by all this?
We have shown L mu star. So we have to show two things. L mu star is sigma algebra. That means it's closed under complements and countable unions. And we have to show that mu star, when restricted to this collection, has the countable additivity property, right?
Yeah, yeah.
But these two claims are not going to be intertwined. So first two are easy. Closed under complementation is trivial. So that is done. Countable union is hard. So first we do countable union and countable. Once you have complements, countable union, countable intersection are the same, because, right? So you can intersection complement is union of the whatever, right? So we will first do finite intersection and then do countable intersection. But after doing finite intersection, we also observe the finite additivity property of mu star. And then we go to the countable. We upgrade it to countability. Okay. First, we will do the finite. First, basically, we will show L mu star is an algebra, and mu star restricted to the algebra is finitely additive. That is what you can say we are going to do first.
Okay.
Okay. So, so let's say I'll write that here. If AB belongs to L mu star and they are disjoint, then mu star of the union. Okay, so first of all, maybe I should say here already. So if AB belongs to L mu star, implies A union B also belongs to L mu star. This is also done because complements and intersections are done. A union B complement is A complement intersection B complement. Therefore, from this we have also done that. So when I write A union B, it makes sense here. So mu star of A union B is actually mu star A plus mu star B. That is, mu star is finitely additive on this. L mu star is an algebra from this what I have done, and mu star is finitely additive on it. Actually, we need a little more. In fact, this is true with a more general thing. Mu star of E intersection this is mu star of E intersection A plus mu star of E intersection B for all E contained in X. So if you put E to be X itself, then you get this. If E is X, then intersection with X is the set itself. So A union B mu star will be mu star A plus mu star B. But it's also true with any subset E. This is true in general. Okay, so why is that true? I think, yeah, so you just use cut condition with, this is my set, right? So I take E intersection with A union B in place of E and A in place of A. Okay, so what will be, so let's call this set D, for example. So what will be D intersection A? E intersected with A union B intersected with A, because A and B are disjoint. So this is just E intersection A, and D intersection A complement is just E intersection B. See, A and B are disjoint, and D is E intersected with, so A is here, B is here, they are disjoint. So E intersection with the union will consist of two parts, E intersection A and E intersection B. That's what I'm saying. Therefore, the cut condition tells you that mu of D intersection A union B is mu of D intersection A plus mu of D intersection A complement, which is what this is. So we have actually shown that, so far what we have done in summary, L mu star is an algebra and mu star is finitely additive. Mu star restricted to this L mu star is finitely additive. Okay. Okay, it's 4:58, so I could rush through the rest, but maybe let's not rush through the rest. I actually rushed it in the first time, saying because I would do it again. If I rush it now saying I did it before, then it's kind of not a good idea. So let's do the countability part next time. So, and then we still have the second claim, which is that mu star, when you start with a countably additive measure on a function on an algebra, this L mu star is big and mu star equal to mu. Still, the question remains, how do I check the countable additivity on the algebra? I mean, it's a bit of a pain. That's a separate question after proving this theorem. But so what remains is, to prove this, I want to finish this countable. We have to upgrade L mu star from algebra to sigma algebra and mu star from finitely additive to countably additive. After that, we'll come to the third claim 2. Okay, so maybe I will stop here. If there are any questions, yeah.
I have one query from previous day lecture.
Yes.
Yes, like in a proof, we were checking 3 conditions. A and B is in algebra, A is in algebra, and B belongs to M of A. And third condition, A belongs to M of A and B belongs to M of A. While proving the third condition,
one second. Which one are you talking about? This one? This?
Yes.
Okay.
This one, yeah.
It's 5 o'clock.
While proving the third condition, we said that this is as before, like previous step. But here, like A belongs to M of A, not like A belongs to algebra. But like how we have said that this is as before the previous step.
Which one? Which is as before the previous step?
Yeah.
Which one? Sorry. Here
that arrow, yeah, by previous step, this arrow, like
No,
A
this is
union B
not
belongs
as in
to.
previous step. This is by the previous step. I am saying ZA contains A. What is the meaning of ZA contains A? That means you take any, say, capital A in this algebra, then it belongs to here, right? Oh, sorry, B. Any B. Let's take a set B in the algebra, then it belongs here. In other words, B is in the algebra, and what is A? A is in the monotone class. So then have I not proved that B union A is in the monotone class?
Yes, sir, that is true. But here B is also in the monotone class, right? Not in the algebra.
No. Why? I mean, so I'm saying when you say ZA contains A, B is in the algebra, right? Not in the monotone class. ZA is the all B in the monotone class such that this happens. But what does it mean to say ZA contains A? What does it mean to say Z contains this element? What does it mean?
Okay. Okay, so ZA is monotone class okay, algebra. So that contains the
You
algebra.
have to take an element here and show that it is here. So an element here you have to take and it is here. So we take an element B in the algebra. We want to show it is in ZA. That means we want to show B union A is in M of A. But B is in the algebra and A is in the monotone class. So A and B are reversed, that's all. B is in the algebra, A is in the monotone class, so the union is in the monotone.
Okay, got it. Yeah, okay. So like we are thinking B is in the algebra, that's why. Okay, yeah, thank you.
Any other questions? Okay, so yeah, so last time's recording I may have not put up, have I? I mean, so that I forgot actually. So I will do that anyway. So okay, so
No, sir, I have the recording was there, but actually I was thinking A and